Hello, I'm Justin Huey. I'm doing problem 239 from the textbook, in which we are tasked with a neutral conducting sphere, which has two spherical cavities hollowed out from it, in which one we have a point charge QA placed in the center, and one we have point charge QB placed in the center. The spherical conductor itself has a radius of big R. So first we are tasked with finding sigma A, sigma B, sigma big R. So surface charge density on this surface, and then on this surface. And we know that sigma is equivalent to the charge over area. So first things first, let's go through and draw. So we know we have this point charge QA, and we know that that's going to induce a charge equivalent to the opposite of negative QA. So we'll just say negative QA. And why is it doing this? So we know that we're dealing with electrostatics. And in that case, we know that the electric field inside a conductor is 0. We know that one way for this to happen is for these negative charges to be induced. And then due to the uniqueness theorem, we are able to say, okay, that is the way it does happen. These point charges are inducing opposite charges on their surfaces. So that makes it simple for sigma A. We could say sigma A is equal to negative QA all over the area 4 pi little a squared. Same for sigma B, we could say that's equal to negative QB over 4 pi B squared. Okay, how about for sigma R? So we know that these two charges, so we know that conductor only has charge on would only hold charge on its surface. So what we know is that, okay, these charges, this negative QA charge and this negative QB charge had to be pulled from the surface, which means that this surface is now lacking those charges. So we could say that now there's a charge density along this surface. Okay, so I'll give the sigma R, which will be equal to, we know the charge is pulled away, so negative QA got pulled away to be here, so leaving positive QA and a positive QB, because negative QB was pulled away to deal with this point charge. There we go. And this will be 4 pi over big R squared. Let me circle this. So that does it for part A. All right, now in part B, we are tasked with finding the electric field outside of the conductor. Okay, well, we know the electric field is equal to 1 over 4 pi epsilon naught charge enclosed over, or just charge, sorry, Q over R squared in the R hat direction. And that's pretty simple. So electric field outside will be equal to 1 over 4 pi epsilon naught, of course. And what would the charge be? Just like we found out for sigma R, the charge would be QA plus QB over radius little r squared in the R hat direction. Why am I using little r instead of big R? Well, because it's outside, so we could say little r would go like this. Let me box that up. And that does it for part B. All right, so in part B, we were able to do this because of the spherical symmetry of the situation. And of course, we were measuring outside the charge density, so we could treat it like a point charge and use that equation. But now for part C, we are tasked with finding the electric fields due to A and B inside their own little enclosed regions. So electric field A. So how would we find this out? So looking inside, so we're looking at the charge only in this region right up until, so right before we get to the surface. And we'll call that RA. So going through like this, RA is in between 0 and A, the radius of the sphere. So of course we know the electric field due to A, 1 over 4 pi epsilon naught, QA over RA squared in the RA hat direction. And we know the same argument holds true for point charge B. But this time it'll just be QB. Sorry, that's a little ugly. And then RB, which of course is in between 0 and B, the radius of the cavity, in the RB direction. There you go. All right, and now we're asked to find, in part D, we're asked to find the force on QA and the force on QB. Okay. So let's go back to our drawing. Okay, so what would the force on QA be? We know that we have this point charge here, and it has its own surface charge that it induced. However, the only charge within the enclosure is the point charge. The induced charge can't propagate into the cavity, meaning that the only electric field in here is due to the point charge, and the point charge cannot act on itself, meaning that there's no force on it. And the same holds true for point charge B. So that allows us to say that the force on both, there you go, is 0. Okay, and then part E is saying, what if we introduce a point charge QC on the outside? So let's say we just had a point charge QC right here. And it's asking us, okay, go through the steps again and what would change? Okay, so let us see. Would sigma A change or sigma B change? No, they're basically within their own little sphere of influence. A point charge wouldn't have any influence on them. Sigma R, however, would, because it would also manipulate the charge on the surface to basically accommodate it. Electric field outside would change, because again, the surface charge density the surface charge density changes to accommodate the point charge, so electric field outside would change. However, the ones inside for A and B would be unaffected, just as the force on A and B would still be 0 in this situation. And that does it for problem 239. Thank you.